Hi, everybody. Professor Leach here. Today, we're going to combine substitution in parts in our continuing series of spending too much time on these two integration techniques. I want to look at substitution in parts and combine them together. This will reinforce our understanding of substitution, and it'll also reinforce our understanding of parts. So help us put those together. Putting those together and making these more difficult problems will help us understand the process in general. So let's take a look at first at this problem. So here we have x, and then we have an e to the x squared. This one needs to stand out. We need to notice this x squared is inside, and then we have to identify this x is going to be the derivative of the inside. So this is a substitution problem. Remember, every time you decide that you want to make a substitution, every time you decide that you're going to make a substitution, if you think you want to do this, oops, I'm getting ahead of myself, w equals x squared. If you think this is something that you want to do, that means you need to find out what's going to be your dw. If w is x squared, then you need to take the derivative. So the way that I'm thinking about it is, if w is x squared, then I need a multiple of x to be the dw. Think about what you need to stand in for the dw, because all x have to become w, and the dx is included in that. The dx must become a dw, but the dx can't become a dw on its own. The dx needs an x attached to it to become the dw. The normal thing that I do here is to take out the 2 and say I have an x dx, and an x dx is equal to a 1/2 dw. So nice straightforward substitution problem. So I usually pull my 1/2 out in front, and we're integrating an e to the w dw. So we've traded our integral dx for an integral dw. So now we can integrate the e to the w. The integral of 1/2 e to the w is a 1/2 e to the w plus c. So now we can integrate the function in w, and then we can go back to our original variable. So 1/2 e to the x squared plus c. Classic substitution problem. It's one we should all be familiar with. This is the wonder wall problem. So anyway, here's a substitution problem. That's what this is. Everybody needs to know this one. Fun fact, I can't play Wonderwall. I can't even picture the song in my head right now. But anyway, here's Wonderwall Mathematics Edition. Everybody needs to know this problem. Let's compare this problem, x e to the x squared, with a variation on this theme, which is parts. Let's say x equals, let's integrate x e to the x, and not squared this time, just an x e to the x. This one we won't want to make the substitution w equals x, because that would just be rewriting x as w, and we'd be in the exact same situation. So I don't have an inside and a derivative of the inside on this one, so we'll have to do parts. Oh dang, I wanted to flip these around. Oh boy, I actually wanted x squared e to the x. So in this case, the x squared can't be the inside because it's just a factor. The x squared in the first problem was inside an e to the x. Here we put the x squared into the e to the x by composition. X squared is inside the e to the x. Here we used composition of e to the x and x squared. In this example, we have a product of e to the x and x squared. So composition means anti-chain rule. Product means anti-product rule. So we're going to use parts. In a parts problem, I want to try to dv has to be something that I can integrate, and I don't want to make things worse. So I'm going to put the x squared in the u column, and in the dv column, I'll put an e to the x. I'll take derivatives down to 0. I recognize that I'm going to be using parts multiple times, so I'm going to differentiate down to 0 using the technique we learned last time. And so for every derivative, I'll write an antiderivative, and they're all going to be the same. Then I'll just form products, all the different UVs going down this line. So x squared e to the x, 2x e to the x, and 2 e to the x. Those are my 3 terms. So I've got an x squared along with this e to the x. Then I have a 2x e to the x. And finally, a 2 e to the x. And I can drop the plus c now. Now remember, we are alternating keep the sign, change the sign. All these terms are naturally positive, but I'm going to alternate keep the sign, change the sign, and then keep the sign. So I'll keep the sign of the first term as positive because it's naturally positive. The second term is positive, so I'll change the sign. The third term is positive, so I'll keep the sign there. So we have our 2 classic examples of integration by substitution and integration by parts. Remember the rules for substitution. The thing you want to remember for substitution is that something's got to be my DW. So in substitution, we've got to remember we need something to be the DW. We need some part of the function we're integrating to contribute to the DW so that we can integrate in W. So when I say all the terms are positive, all the terms are naturally positive. X squared e to the x, 2x e to the x, 2 e to the x. But it's keep the sign, change the sign, keep the sign. We alternate keeping the sign and changing the sign. Because it's uv minus the integral of v du. And so that minus will go before another part. So it'll be uv minus the parentheses, uv minus parentheses, uv minus, and so on. So that's why we alternate keeping the sign and changing the sign. So in substitution, the main thing that we need to remember when we do integration by substitution is that something needs to be the DW. In parts, dv needs to be something we can integrate. So those are the 2 big things that we want to keep in mind when we're doing either of these techniques. dv must be something we can integrate. So let's look at a problem, a variation on this theme. Let's look at a problem. All right, oops, I'm gonna need to move some stuff. There we go. Where we have to combine these ideas. We have to keep that, they'll emphasize keeping these big rules in mind so that we're not just following a process, not just following the process, we're understanding how the process works. It's important that we understand how the process works so that we can see when the process isn't working. We have to know what's supposed to happen so that we can understand when it's not happening. So I'm going to look at this example. If I just have, let's say, e to the x squared, let's just review our thinking. If I have an e to the x squared, I can't do a substitution on this problem. There, x squared and e to the x have been combined with composition, but I can't make the substitution w equals x squared because I don't have anything left to be the dw. That's how we want to think about this problem. So we can't make the substitution. There we go. We can't substitute w equals x squared because we don't have anything left to be the dw.
So you're saying that if there was like another value in front of e, like 4, then that could be dw, or it has to be something with x?
It has to be something with x.
Got it.
Because the substitution w equals x squared needs a dw
Got it.
of 2x dx. The 2 is not important, but the x is important.
Got it.
I need an x to be that dw. So that's why substitution was fine up here, because I had w equals x squared. This x out here can stand as the derivative of the inside. That will contribute to my dw. This e to the x squared without that x, I don't have anything to be the dw. So this substitution is not going to work. We have to understand when substitution ain't gonna work. Otherwise, we'll just assume that it does and get things wrong. So let's take a look at a problem what we've seen before.
Professor,
So we know, go ahead.
I just wanted to ask a quick question. So then what would we do for e, for that last example? We couldn't use parts or substitution?
No, we don't have an answer for this one.
Okay.
Right now we're stuck. Actually, this e to the x squared, it does not have a nice antiderivative. So we'd have to construct one with the second fundamental theorem of calculus.
Got it. Okay.
So let's take a look at another example. Let's look at x squared e to the x squared to x. So in this substitution, in this problem, we'll notice that there's an x squared and an e to the x. There's a composition, but that x squared in front is also included with as a product. Sentences are difficult to put together today. I'm glad this is all getting recorded. So if we make the substitution, if we want to try the substitution, w equals x squared, at first it seems like it's going to work. dw is 2x dx, so a half dw is an x dx. We need an x to be the dw, and we have 2 of them. So it seems like it's going to work. We can split this x squared into, well, there's an x going to be left over. I'm going to save one of the x's to be the dw. So this x here can be the dw. And then we multiply by e to the x squared. This x squared up here is going to be my w. So this x dx can make my 1/2 dw. But now I don't have an answer for this x over here. So I can make the substitution w equals x squared. I have an x to be the dw, but I've got this extra x that I don't have an answer for. So what we're doing here is one of these x's can be the dw. So that's good. One of these x can be the dw, but I need an answer still for this extra x, what we do with this extra x. So we don't have an answer for that. Remember, the other thing about about integration is that in an integration by parts problem, we can't make things worse. So let's put a pin in this problem. Let's remember this x squared e to the x squared. We kind of got stuck on substitution here. Let me look at another problem to see where substitution will work, and then circle back to this problem. This is going to be a fun day in calculus, because I think most of the integrals I'm using for examples today don't work with the methods that we're learning. So it always makes for a very fun math class. It's like, oh, let's do a bunch of examples where you don't know how to do them. And then the students be like, are you going to tell us how to do them? I'm like, oh, no. I'm just going to put them in front of you and make you suffer while you watch them. What is it? Week 5, day 2. So let's keep that x squared e to the x squared in mind and look at and push things a little bit further back to where they will work in kind of the standard way. Let's look at x cubed e to the x squared dx. So what stands out to us in this integral is that there's composition again. X squared is inside an e to the x function, and there's also a product, x cubed times this e to the x squared. X squared inside, that composition tells us we should try substitution. Because I don't like e to the x squared. We know that that doesn't have a nice antiderivative. So let's try to substitute our way out of that. Our instinct might be to say, let's make w equals x squared. Because it's sitting inside an e to the x squared, I would rather be writing e to the w. The question becomes, can I get away with that? If I want to make the substitution w equals x squared, I need an x to be the derivative of the inside. So if w is equal to x squared, dw is 2x to x. So a 1/2 to w is an x dx. And we knew this before we started because that's been the theme for today. If w is going to be x squared, then I need a factor of x to be the dw. And we look at this problem, we say, great, I've got 3 factors of x. Got a lot of extra this time. I'm going to separate out 2 of them. And I'm going to have to come up with an answer for that. I'm going to save one of these x's to be the dw. The x squared inside the e to the x is going to become the w. I haven't done it yet, so I'm just going to mark it in orange. And then x dw, sorry, x dx is going to be my 1/2 dw. So just like in the previous example, I'm going to save one of these factors of x to be the dw. So let's keep one of the factors, one of these, x, to be the dw. But just like before, I still have to come up with an answer for this x squared. This x squared inside the e to the x is going to be the w. This x and the dx are going to combine to make a 1/2 dw, but I've still got to replace this x squared, and well, isn't that convenient? So since I'm left with 2 factors of x, I've been replacing 2 factors of x with w this whole time. So I can replace this x squared, I can easily replace with a w. So we still have leftover x squared. So that's us being happy that everything is working out. So that this x squared out in front, that's going to be one factor of w, not inside the e to the x, but it's going to be a w. X dx is going to all become a 1/2 dw, which I conveniently didn't give myself enough space for. So the 1/2 dw comes from x and dx. X dx is 1/2 dw. And then my function is the e to the x part, sorry, the e to the x squared part will be written as e to the w. So I've traded all my x for w. And I can integrate we to the w because we had just done that. Well, we did that as part of doing a larger problem. So we have substituted our way into a parts problem. So like I said at the top, this is substitution and parts. We substituted our way into a parts problem. So when we look at 1/2, the integral of we to the w, we can set up parts where u is equal to w and dv is equal to e to the w. Then du is 1 and v is e to the w. And we should notice that our u will differentiate down to 0 while the dv column just stays e to the w. So I'm going to differentiate this all the way down to 0. For every derivative, I need to take an integral or an antiderivative. Then I'll make products down diagonals, we to the w and 1e to the w. I have integrated, so that's when the plus c shows up. And I'm going to alternate, keep the sign, change the sign. The first term is naturally positive, so it stays positive. Second term is naturally positive, so I change it to negative. But we don't put a box around this answer because this is the integral in w. This is all inside of a larger substitution problem. I have to go back from w to my x. So just replace the w's with x squareds. Oh yeah, I'm going to do this down here. So I'm going to replace the w's with x squared. So w is x squared, e to the x squared, minus e to the x squared, plus c. If you wrote this for an answer, as long as the parentheses were all in place, that's fine to leave the 1/2 hanging out there. If you multiply the 1/2 in, that's pretty good. Although there's that e to the x squared hanging out inside the parentheses. So probably a better way to write this would be to factor out the e to the x squared and write this as 1/2 e to the x squared times x squared minus 1. In this case, it's probably better to write the polynomial after the exponential function, since the polynomial is going to be in parentheses. If all I had for this polynomial was an x squared, then I would want it to be in front of the e to the x squared. That's just style guide stuff. So that's part of the style that you'll just eventually pick up as you go through, and not part of the process, which is what you're actually trying to learn at this moment.
Professor, from the previous equation where it says now we use parts, how do you know now we're using parts? Like, what if someone just wrote that as the answer?
Well, this function, this still has an integral in it. I said find the antiderivative. We still haven't found an antiderivative.
Got it.
There's still stuff to do. Only when you take the step and when you get rid of the integral and the dw and write a plus c, that's when you have integrated things.
Got it.
Then you just have to make sure that your answer is in the correct language. It started off as an x integral, so your function, your antiderivative needs to be an x. Any questions? I want to look at this problem in another way, because I looked at this problem and I immediately thought of substitution. Because when I saw this problem a long time ago, in the before times, way back when, talking like early 90s, that's what I saw. I looked at this and I saw x squared inside the e to the x function, and I said, substitution. But that might not be the first thing that you see. You might see the x cubed times e to the x squared and think parts. Because what you're trying to do is you're looking for a composition. If you see a composition, that should make you think of substitution. If you see a product, that should make you think of parts. Because a composition, or the chain rule is for composition, and the product rule is for products. Substitution is the anti-chain rule. Parts is the anti-product rule. So I saw this first as a composition, and so that's why I went after it with substitution first. Then when I did my substitution, I said, well, now I need to use parts. Some of you, when I first looked at this problem, saw the x cubed and say, that's my u. I want to differentiate that down to 0. And so you saw this initially as a product. I don't know which camp you fall into. If you had a professional teacher, he could have had like a Zoom poll. It's like, oh, and before I even did anything, before I poisoned the well like this, I said, is this substitution or parts? And then some people wouldn't have answered because they're like, oh, I don't want to lose points. Michael, it's no points. Like, well, I don't want to lose. I don't want to get the wrong answer. But then I would reveal the results and they say, haha, it's both. So let's suppose that we saw this the other way around. What if we saw this? What if we saw a product first? What if you saw a product first? You didn't see this as a composition first, you saw it as a product first. And if you saw it as a product first, you're thinking integration by parts. This one. So that is, so when I say you saw a product first, you're thinking of integration by parts. That's fine. We saw in this problem, both of them showed up. So we're looking at x cubed times e to the x squared to x, and you saw it's a product. That's parts. Let's see what happens when we start using parts. So it's parts, and then in my u slot, I'm going to put an x cubed because I want to differentiate that down to 0. But here's where we run into the problem. In the dv column, that leaves e to the x squared. I'm going to mysteriously start including the dx in that part as well. And here's where we run into a problem. Here's why we don't want to just go on autopilot. Well, we have to look at things and decide if they're actually working or if we're just faking it. Here's where we run into a problem. Leach's first rule of parts is that dv must be something we can integrate, and we don't have an integral for e to the x squared all on its own. dv must be something we can integrate. So this is not going to work. So we can't put e to the x squared in for dv because we don't know the antiderivative of e to the x squared. If you're thinking about dividing by the 2x, you can only multiply and divide by constants. And if you're still not convinced by that, look at what you wrote for v, take the derivative of it using the product rule, quotient rule, and chain rule, and see that you do not arrive back at the e to the x squared. It's not that we haven't found the antiderivative of e to the x squared. There isn't one. It's like, it's not that we haven't found a ratio that makes pi, a ratio of integers that gives us pi. We've proven that there isn't one. So it goes further than that. So the problem here is that e to the x squared is not something that we can integrate. But what we can integrate and that we have available, if we have an x and an e to the x squared, oops, that's this one. If we had x e to the x squared, we can integrate that. If we have a factor of x to be the dw, then we can integrate an e to the x squared. So that's what we want to observe here. I can't integrate e to the x squared because I can't do a substitution. W equals x squared requires an x to be the dw. But if I move an x from the x cubed over to the dv slots, then I can. So what we're going to do we're going to move a factor of x from the u column to the dv column. We're going to perform a slick maneuver. I'm going to break up this x cubed as x squared times x, and I'm going to move one of these factors of x over into the dv column. And then u is going to stay x squared. Raise an important question. Why would we do such a thing? We noticed that we could not integrate e to the x squared on its own. I can't do a substitution there because I need a factor of x to be the dw. Then that's what informs us to do about the slick maneuver that we performed. I can integrate e to the x squared by substitution if I have a factor of x to be the dw. So let's go over to the u column and shift a factor of x over into the dv column. Now we can integrate. Now I can differentiate du is 2x. And the integral v we can do by substitution. This is going to be a 1/2 e to the x squared. See the first example for that substitution. That's why I led with that example, so I could call it back here. Now, I just need to integrate with the parts formula. I'm still got to remember I'm doing parts. So I'm going to do uv minus the integral of v du. So the parts formula says, do u times v minus the integral of v times du. So u times v is going to be a 1/2 x squared e to the x squared minus the integral of 1/2 e to the x squared times 2x. Oops. We can cancel out the 2's. And so we're integrating an x e to the x squared again. But we have the integral of x e to the x squared. It's a 1/2 e to the x squared. So now we can do our last integral. This is 1/2 x squared e to the x squared minus a 1/2 e to the x squared. And we've integrated so we could plus c it. And this is the same thing what we had before. We could factor out a 1/2 e to the x squared, and it leaves behind x squared minus 1. Or we could just halfway it and factor a 1/2 out of the first 2 terms. I factor a 1/2 out of the c because the c is an arbitrary constant. Notice that in both times we attempted this problem, we had to do a substitution and we had to do a parts. And also notice that if we keep our rules in mind, if we remember that if we're going to integrate by substitution, we need something to be the dw. If we remember that dv needs to be something we can integrate when we're doing parts, doesn't matter which one happens first. We can substitute our way into a parts problem, or we can parts our way into a substitution problem. So that's great. There's more than one way we can approach the problem, but that's also terrible. There's more than one way that we can approach the problem, which means we have to decide. Any questions? All right. We're going to finish up looking at finish up looking at substitution and parts tomorrow. We've got to keep all of our tricks in mind because in the future, when you're working as an engineer, you're going to have to do a lot of integration by hand. I'm just kidding. You won't have to do that. If ever comes a point where you have to perform integration by substitution or integration by parts, and you have to do it by hand using the techniques that you learned in this class, go ahead. I need you to send me an email with a video of your boss telling you that you have to do this by hand. And it cannot be in the context of the boss says, my kid's in calculus, tutor him. That doesn't count. Any questions? Comments? Changing variables, though, that'll happen all the time. I don't know if you'll be doing it by hand because I don't know what it is that engineers do. They just make stuff that breaks as far as I can tell. Any questions, comments, snide remarks?
Might be a dumb question, but how do you know when to stop integrating? Because
the integral, so I stopped integrating here because I said, okay, now I'm going to take care of this integral. This integral is a substitution again, so I just did the same thing that we did up here, which is the same as the original. I've integrated something, so now I'm done. It's the same way we decide to stop when we're doing differentiation.
Okay.
There's no sign that's going to pop up. So my my glib answer that I usually use is like, you'll just know. Any questions? Comments?
Yeah, I have a question. So when you keep integrating, you want to keep going until, like, for that example, it would be until x was to the 0 power, right? Because then it's just, then you don't have to integrate anymore.
No. Notice that I did not, even though x squared will differentiate down to 0, I did not do that in this problem. Because if I wanted to do that, if I took another derivative, I would have to find another antiderivative, but we don't have an antiderivative of 1/2 e to the x squared. It stops right there. I can't do that continuation where I just differentiate down to 0. I can't use that trick because I need to integrate for every derivative, and the integrals have to stop here. If I have a factor of x here, then I can integrate this. But once I've used that factor of x, I can't just start shifting things over. I can only start shifting things over at the very beginning of my parts process. Can't just start moving things over.
Okay.
So I could not differentiate down to 0 because I couldn't integrate the e to the x squared anymore. Any other questions? Rad. All right, we'll look at more of these problems tomorrow. There is one still hanging over us. You still go, hey, what about this x squared e to the x squared? I want you to think about what happens, what we can do with that x and see if that's going to help us, and see if that, or see just what kind of problems the solution that you thought of would create. So right now I'm leaving you with this open question, because some of you are thinking, can't I do this? And then you have a thing in mind to do with this extra x. And my answer is going to be, at this point, no one asked that question, but sometimes someone will, because you didn't want to think about it. But you're going to ask the question, it's like, oh, can't we just do this with this extra x? And my answer would be, I'm just going to tell you what my answer would be. I don't know. Can we? And then that's your cue to go and find out if that trick that you thought of would work. All right. A little bit overtime today. I started a little bit late. Sorry about that. So thanks for playing. And until next time, peace out.